Okay. Okay, should be good. Hopefully everybody can see the slide deck. Let me start it up. So I'm Jason Horner. This is Isn't That Spatial? An introduction to SQL Server Spatial. Really cover things in 3 different parts here. We'll go over basic spatial concepts that everyone should know before they kind of start working with this data. Then we'll look at some basic ways that you can manipulate and query data from within SQL Server. And finally, we'll look at some ways that you can consume it from .NET-based clients like C# or perhaps PowerShell. So let's keep moving. Oh yes. Bear with me for a moment. I've been having trouble with my PowerPoint. I can try to restart this. All right, it should be going now. So just a little bit about me. Jason Horner, Microsoft Certified Master. Apparently that doesn't hold to transfer over to PowerPoint, as you can see with the crashes. Worked at a couple different companies over my career. I'm currently at Digital Globe. We take satellite imagery and make pictures like you see at the bottom. The picture on the left here is a picture of my house from Google Maps using our GeoI, our Digital Globe imagery. And a picture of the right is our family farm in Minnesota. So my contact information is up here. If you have any questions regarding spatial data, PowerShell, data warehousing, feel free to send me an email, connect to me on LinkedIn, or send me a Twitter message. So spatial data really is about solving problems. So proximity, how close are things to each other? You know, if you want to get a pizza, where's the closest place I can get a pizza? Looking at change detection in terms of crops or other things, trees, vegetation, those kind of things. Trending analytics, you know, where are stores located, where are they not located anymore. Route finding, finding the quickest path to a given point from a given location. And then visualization, of course, that's kind of the new trend right now in the BI spaces. People are really starting to get into using the different mapping products like Tableau and GeoFlow to see their data spatially on a map. So, of course, the solution to this problem is spatial, right? And you can ask yourself, well, I don't really have any spatial data, but everybody probably has address data, right, so on and so forth. And even though maybe it's not a big part of your line of business as you think, you can see from this list of industries that you probably do have a lot of spatial, and there's a lot of use cases for using spatial in these different things. Everywhere from, you know, where do I plan to put my stores, you know, telecom, what's my cell phone coverage look like based on the given towers I have. I know a person who works in a mortgage industry, and they use it to take a look when they go to do a mortgage on a piece of farmland to see, you know, to take a look at the land and make sure it's viable for farming before they, you know, release funds for new loans. So there's lots of different ways you can use spatial, and we'll kind of get into some of the nuts and bolts. But just want to show you some more imagery that our satellite takes. This is imagery that has been what's called orthorectified, and that gives it that kind of 3D perspective. So you can see it's really powerful to get spatial information and then, you know, overlaid imagery on top of it. Again, this is a picture of, we use it for crisis response, for change detection. And then basically what we do is we take satellites and track imagery and produce those. So to understand spatial, the first thing you have to understand is coordinate systems. And there's really 2 types of coordinate systems. There's geographic coordinate systems, and that stores the data in a round or spherical model, and it relies on latitude and longitudes. And in SQL Server, that maps to a geography data type. Then there's also a projected coordinate system, and that's something similar to what Google Maps or Bing Maps would use to show data. And it's a flat model, and it relies on X and Y values. And in SQL Server, you would use the geometry data type for that. So diving a little deeper into coordinate systems, obviously you have latitudes, which run north to south from 0 to 90, -90. And then you have around the middle of the Earth, the equator, right? And then you can also, you'll hear these referred to as parallels. Then you have longitude, which runs east to west, 0 to 180 and -180. And that has a prime meridian. And it's important to note the prime meridian is really defined based on the projection system. It's kind of arbitrary. So the prime meridian can change, whereas the equator is always the equator, right? And then the longitude lines are known as meridians. A couple different ways you can represent latitude and longitude. You can use decimal degrees, like this 3961 latitude and -105.06, or you can use degrees, minutes, second notation. You'll find this a lot in topo maps, atlases, and Wikipedia articles. When they reference a location, they typically put it in degrees, minutes, seconds. And then another thing to note is that the actual area of a given 1 degree by 1 degree cell in latitude and longitude changes throughout the Earth, and that's why you need that spherical model. We'll show a little bit more about that, but the point being is that the areas are much larger here towards the equator than they are up towards the top. Again, this is just more kind of scientific stuff about the projection system, and it's just basically to show that what we do with the geographic projection system is we take the geoid, which is really just a model of what we think the Earth looks like, and then we map an ellipsoid that's kind of a best fit approximation across that. And obviously there's undulation there for where the ocean surface is, where mountains are, so on and so forth, and we try to find a good approximation that we can model it. It's interesting to note that WGS 84 or WIGS 84 is currently the projection that they use for GPS type systems, and it's a very good generalized model of the entire Earth. But there are other models that are more accurate when you're looking at just a specific area of the Earth. Say, for example, the United Kingdom or the United States. There's different projections that you would use that would give you a better accuracy over those areas specifically, but not necessarily applicable to the Earth as a whole. So just again, datums are comprised of ellipsoids, and they can be geocentric or local, which is kind of what I just talked about. And then it's easy to get them mixed up. Sometimes they have the same name, but they don't necessarily mean the same thing. So now, why is that hanging up again? Yeah, great. I'll restart this real quick. Yeah, I think we're here. So other components, you have prime meridian and unit of measure. And again, just another model of what the geoid looks like and how those different curves match up. The projected coordinate systems are much simpler, and they're just based on X and Y coordinates, and they're equally spaced. So a good way to kind of conceptualize the difference between these two is when you're dealing with a geocentric, your model is actually round, and then it gets projected to a flat display. When you're dealing with projected data, your model's flat, and it gets projected to a display. And the different projection models will have different distortions, either within the area, direction, distance, or shape. And these are just some of the different types of projections and how they go about best fitting the given model of the Earth. So what we can do is go into some demos. So SQL Server stores the projection metadata in this Spatial Reference Systems table, and we'll look at some common ones here. One thing to note, although it's not hugely important, but I am using a Windows Azure database, so even though the Azure database themselves don't support CLR, it does support the spatial data types. So You can see here that we have the different threads. So 4326 is the WIGS 84, or the model that the GPS systems typically use. And it's got all of the information about that projection embedded in here, as well as the unit of measure that it uses. And then I just kind of was curious, is there anything that doesn't use a meter projection? And it turns out that there's a few of those in here. So we can kind of see that there's a couple of them. Now notice that all of these are geographic projections. There's no projected data stored in the sys references schema. So we'll go back over here to the deck. Okay. So SQL Server Spatial Architecture, there's UDTs, so user-defined data types based on .NET CLR types. There's a geography, which you use for the round Earth model, and geometry, which you use for a flat Earth model. This diagram over here kind of shows the hierarchy of the object model. This object model is actually published by the OGC, and it's known as Simple Features object model. I have a link later in the slide to where you can look at that. But it basically defines the different types of geometries that you have. You have points, line strings, polygons, and then the collection types. And we'll dive into those deeper here in a moment. Now, since these are .NET object types, all the properties and methods on them are case sensitive, and they're available in all SQL Server editions, meaning Enterprise, Developer, and Standard, except for Compact, but they're not in all versions. So the spatial support was introduced in SQL Server 2008, and there's some significant enhancements in 2012. I'm not sure if I don't think there have been any enhancements to the spatial support in 2014, but I don't think the bits have dried on that yet. And then just some internals about the spatial data types. They're stored as binary, so there's about a 2 gig storage limit. And then the precision, it stores it out to about 15 decimal points of precision. So some of the methods will take more than 15 decimal points of precision, but anything beyond that usually gets truncated. And then when you do spatial calculations internally, SQL Server uses a grid, and it snaps those points to a grid. In 2008, it was a 27-bit grid, and in 2012, it was a 42-bit grid. So there's a lot more. You get a lot more accurate precision moving to 2012. And we'll go into some demos of this, but this just shows you the different methods on the different geometry and geography objects. You can take it from text, which is well-known text, well-known binary, and then you can put those back out. And we'll actually talk about what those well-known text and well-known binary and other formats like GML are when we go into the demos. So the spatial objects have properties. So you have what type is it? Is the geometry empty? What's the centroid, envelope center, the length, the area, so on and so forth. Spatial point properties. So points have specific properties like the lat and longitude. And then two kind of overlooked things that I think people don't use much in points are the M and the Z value. So the Z value can define an elevation of a given latitude and longitude, so an object, but the measure can store some kind of arbitrary numeric value. The measure isn't used in any kind of spatial calculations. It's just kind of metadata that's stuck with the geography or the geometry or geography object. So you could for measures, for example, you could use, if you're storing points that represented stores, it could be the square footage of the store, and then you could access that square footage just by referencing the M value. And then you have some other methods like getting the number of points if it's a geometry, getting the start point, getting the end point. We'll have a demo of that later as well. Then there's methods to test spatial relationships. So if two objects intersect each other, if they're completely disjoint, if they overlap, if one completely contains, what's the distance, the shortest path, and then if two objects are equal. So we'll go here to the demo, if it doesn't crash again. All right, we'll move back over to the demo. So, demo 2. So we'll look at creating some geometries very simply. So first thing I'm going to do is log into my spatial demo database. I'm going to drop the existing table. I'm going to create a table that I'm going to store some point data in. And you notice the keyword I'm going to use is this geography keyword, and that just says that I'm going to store a geography type in here. I'm also going to create three computed columns, one each for storing the latitude and longitude. And notice that it's actually using the .NET methods, or I'm sorry, it's using the method of the geography point here to get the latitude and get the longitude. And then I'm also going to store the well-known text by getting the STS text method. And I'm going to create a primary key. It's important to have a primary key on your spatial tables, because if you don't have a primary key, you can't create a spatial index. And oftentimes spatial index, especially when dealing with large point data sets, can greatly increase performance. So I'm going to go ahead and create my table. Okay. I'm going to go ahead and insert 3 values into the table. And notice I'm populating it in 3 different ways here. So the first way, I'm using what's called the point constructor, and it's a static method, note the 2 colons here, of the geography object. And it takes in a lat, a longitude, and a spatial reference ID, or a SRID. So the SRID for WIGS84 is 4326. The other way I'm going to do this is I'm going to use what's known as well-known text, using, again, a static method of the geography object, and I'm going to specify a point. Now, it's the equivalent point that I'm doing up here, but note that the order here is different. It uses long, lat, and then SRID. So it's reversed to here. So depending on which method you use, the ordering of these inputs may change. And then here I'm just showing kind of a shortcut method to store an empty point. So let's insert that data. It's all pretty good. Now let's look and see what we got back. So I always find this kind of interesting. Notice here that I get this binary representation of the points. I get my IDs back. And then here I'm running those computed columns, so I'm getting the latitude, longitude back. Notice for the empty point, it's null. But only Microsoft could use more storage space to store an empty point than a populated point. I'm not really sure how that works out, but that's just kind of the magic of Microsoft, I guess. So with that being said, let's put some constraints on this. It's really important when you design structures in SQL Server to store spatial data that you put constraints to make sure, just like you would in a normal relationship, that the data in there is what you think is going to be in there. So just like I can put constraints on a value to make it not null, or to make sure a number is in a certain range, I can put a constraint on the SRID and say I only want to store data that's in 4326 or WIGS84 format. SQL Server will let you store geographies that mix and match different projection types in the same column, but if you want to perform any calculations against them, they all need to be in that same spatial reference ID. So I'll put that constraint on. And then I'll also check and make sure that I only want to store point data in this table as well. Now, I could potentially be working with polygon data, and maybe I only want to store that. I could put a constraint based on that value. This just really makes it, makes it sure that I'm only dealing with point data, so I don't have to worry about getting a polygon in there. But also, the optimizer could potentially pick up on the fact that these are only point data and potentially choose a more efficient query plan. So it's best practice, if you know that you're only going to have point data in a table or data of a specific type, to put a constraint there to prove that. And then just to show that, yes, the constraints actually work, we can go in and we can see we get the constraint violation message here. And again, if we try to put an empty polygon. Oh, the problem with this one is obviously the SRID was changed. Whereas this one, I'm going to try to put a polygon in the table. and that didn't take either. So if we go back here and rerun my query, obviously we'll have 3 values, right? So that's a little bit about creating tables to store the spatial data. So here we're going to go in and look at creating some spatial objects, and I'm going to define a varchar max value to store the WKT. In this case, I'm just going to work with a point, and I'm going to show you guys what the different properties return from a geometry and a geography. So I'm going to run that. And I just use kind of a trick here to union the two results of the queries so I can see them side by side. The first row is a where did that go? The first row is a geography and the second row is a geometry. So notice that for points, I've got my binary representation. Oops. I've got my WKT, my WKB, the size, whether it's simple or not. Notice that that property doesn't exist for the geometry. I've got X and Y values if it's a geometry. Otherwise, I have lat and longs if it's a geography. It's of type point, and obviously a point has no length and no area. One thing I didn't show is when you have data returned that's in spatial format, you get the spatial results tab. But notice it's really hard to see the point data here. You can't see the points very well. What you can do is you can put a buffer around your point data to visualize that. But this isn't really meant for something that an end user would see. This is just while you're writing your queries to kind of visualize it, and it can help with troubleshooting or other diagnostics. And I'll show a better example of how to configure that when we get to the polygon section. So next thing we'll look at is a line string, kind of going with the same approach we took before. So you can look at that. Now notice WKT is now changed to line string. We don't have any values for the X and Y or the lat and long because those properties don't exist on a line string. It's a line string, but now we have a length property as well as an area that's populated, and we also have an area that's 0 because obviously a line doesn't have area. And sometimes somebody may try to construct a geometry based on a set of line strings. That won't have any area. The only way to construct a geometry with area is to use a polygon type, which we'll look at next here. So we'll create a simple polygon using the well-known text. Notice that now it's a type polygon. We have length because there's length around the perimeter, 187 kilometers, and we have area of about 2,000 square kilometers. Now notice when I got the data back, I had to convert it, and what I'm doing is I'm multiplying it by 10 to the negative third to go from meters, which is the unit of that projection system, to kilometers, and 10 to the negative 6 to go from meters to square kilometers. So it's important when you return this data back that you put it in the units that the consumers are going to expect. And then just a real interesting little recursive CTE I created here that basically takes a WKT polygon and then counts the points, but then it's going to show each of the points. And you may ask yourself, why would I want to do that? So you can see here it starts with 0 and it goes to 5. There's 6 points, right? And it goes latitude, longitude, longitude, so on and so forth to make the perimeter of the polygon. And notice that the starting point is always equal to the end point. So there's always, for a polygon, you're always going to have at least 4 points, right? So you have the begin and then the vertices and then loop back around to the begin to close the polygon. If you don't have a closed polygon, you'll get an error message back from SQL Server. Now, the reason you do this is it used to be that in some tools like Tableau, and I still think it might be like this, they could work with latitude and longitude and point data pretty well, but they didn't really understand polygons. And so what you almost had to do is, if you wanted to render some custom polygons, you had to return it to Tableau as a set of latitude and longitudes so that it could then visualize that polygon for you. So that's kind of why I created that when I was playing with Tableau. So that's demo 3, and we're gonna look at some relationship testing with demo 4. So what I've done here is I've actually loaded some data from a shapefile. We'll talk a little bit more about shapefiles and how to get them and so on and so forth. For right now, all that matters is that I have this spatial data inside of SQL Server tables. So I've got a subdivision table, and I'm gonna find South Jefferson and declare that as a variable, and then I'm gonna run a couple queries against it. So the first thing I'm going to do is I have a point landmark table, and I'm going to say only return the point landmarks where the point geometry intersects the South Jeffco subdivision. So the intersects equals 1. And then I'm going to actually union that with the South Jeffco polygon, and then I'm going to buffer. I'm going to take the envelope center, so that's basically the center of this polygon, the South Jeffco polygon, and I'm going to put a 10,000 square kilometer buffer around it. So that's a real basic query pattern that you'll get in SQL Server. And it's probably going to be a little bit slow, or maybe a lot of bit slow. And the reason that is because I didn't put any indexes on these tables. So we'll let that crank. There we go. And now the spatial results will come up here in a minute. So here you can see this blue is the outline of the county, and then we've got this buffer around the South Jefferson feature, and then all these little points here are the different points of interest. Now, one thing to note with the spatial viewer is you've got some options here. So you can zoom in, right? I could turn the grid lines on and off. I don't want to mess with the projection since this is geographic data, but I can pick the spatial columns. So if I had multiple spatial columns in there, I can select a different one. In this case, I can't choose a label column, but if I had a column I wanted to label it by, I could pick a label column, and that's just because there's only one other column in the data set, so SQL Server knows that there's nothing to label there. So let's go back here and look at a little bit more of a complex workflow using two terms, dissolve and clipping. So dissolve just basically means take a bunch of polygons and dissolve those into a single polygon, and clipping means take a polygon and clip the area to that polygon. So in this case, I'm just going to get my my red rocks from the point landmark, and I'm going to show any roads that intersect that. And here's the roads, and here's my spatial results. And so it's not a great visualization, but the one thing it does show you is that you can visualize your line strings. And then notice that now I can select, and I've got labels for my different highways and so on and so forth. So move down to something a little bit more interesting. Let's see. Get this down here. So in this case, I'm going to just build this up in pieces. So the first thing I'm going to do is I'm going to take a couple different subdivisions and bring them all together in a single visualization. So I've got Northeast Jefferson, Central Jefferson, South Jefferson, and Golden. So we're going to look at those, and you can see all of these together make out the county outline of Jefferson County, right? And if I turned on the labels, you would see that we now have labels. Now, this is an interesting issue with some of the labels. You see if I hover over this polygon, it tells me that it's Northeast Jefferson, but it doesn't render it, and that's because we're not zoomed in far enough. So that's way too far probably. So as you change your zoom level, you should notice the labels start. So as it has space to write the labels, it can label it. So this is exactly why, and other than the fact that you can't give this to an end user, it's really only useful for when you're writing queries. So there's other ways to visualize stuff by using like SQL Server reporting services with the Big Maps control, or Google Earth or Google Maps or Bing Maps, so on and so forth. So to kind of complete this demo, we're going to go in here and we're going to grab the roads close to Red Rocks Amphitheater. We're going to grab the landmarks, we're going to grab our county, and then the postal codes. We're going to bring that all back into a single query here. So we need to declare this guy, bring that in, and let's see what we get here. So let's look at our spatial results. It'll probably take a little while for this to render. I'll actually bring it up here so we have a bigger view. So that'll probably churn for a while. So Gabe, I've been going kind of fast. Have there been any questions at all?
There hasn't been any questions posted, but if anyone has or wishes to take a moment here to ask any, but so far you're doing good.
Okay, cool. So while this is coming up, we'll just zip back over to the PowerPoint here. Let me re-pull that up. See if we can get it going without it crashing again.
Yeah, Jason, we just got one.
Okay, cool.
Hold on. Let's see. It says. So it says, what are some of the cases for storing multiple SRIDs in one column?
I would say it's maybe in like an ETL situation where you're just bringing the data in and you're staging it or you're landing it down for some reason, and then you just want to store it in one table, and then maybe in your data processing routine you would then break those out into specific tables. In general, I mean, your application usually works with a single thread, right? So usually it's WIGS84. Occasionally, if you're doing data for like a state or local organization, they may have a specific projection that they use. Like I know some folks that were doing a consulting project for the state of Oregon, and there was a projection that they were using that was a standard because it was very accurate over the state of Oregon, right? So it's usually based on what data sets you're working with. So, and we'll talk about how we get those data sets here in a second. And I don't know why this query is taking so long, but while it's turning, we'll kind of dovetail into, okay, well, so how do you get go ahead.
Yeah, and there's one more then, since
yeah,
that's
sure.
still rendering, yeah. And it has to do, basically the question is, can you talk a little about the spatial indexing best practices?
Yeah, so I've got a section that we'll cover for that. We won't dive really deep into it, but I've got a good link at the end of the session for that. And then also there was a session at PASS maybe 3 years ago that Michael Rees did. That was a really great session that actually went into the deep internals of spatial indexing and how it works. And I just recently saw a blog post on the CSS SQL Server CSS support site where one of their team members had a really nasty, really large polygon table, and he went through the process of how he used extended events to diagnose where the index rebuild was taking, I think something like 48 hours or something like that, and he got it down to 4 minutes, which is more on the index rebuild side, but we'll talk more about that in just a sec here. So let me just see if that, okay, so it came back. So you notice here we've got our Jefferson County, right, and we've got our zip codes, So all these different splotchy areas here are the zip codes. We've still got our roads, right? And then, oops, I may have messed that. Oh, I was playing with the buffer last night. So you're not going to be able to see the buffer show up because it's only a 5-meter buffer. But somewhere in here, there's a buffer. Here's an interesting thing that I found kind of while digging in the data a little bit. So we have, you know, these polygons that we got from our census data, our Tiger data, and we've got these areas, but here we've got this empty space here, and it truly is an empty space. So it's like they laid out this county, but here you have these little kind of incursions into the county, and it turns out that actually my house is like probably somewhere in here, probably like right here. And what's funny is this here, and this is a neighborhood in Colorado called Grant Ranch, and it's actually a subdivision of Denver. And this is Denver is a county as well as a city, and so I'm actually in Littleton here in 80123. But this is all where Denver has basically annexed this land, and the reason they did this is there's all these I don't want to call them ponds, but they're not reservoir. I guess one of them is a reservoir, like up here. So they did it to grab this water rights, basically, and then they built a nice subdivision here to use all the water. So I just thought that was kind of interesting how when you start looking at the spatial data kind of from more of a macro level, you can see these kind of interesting things that happen. So just kind of an aside. But anyway, so getting back to obtaining the spatial data, so obviously, I mean, you're not going to sit there and just arbitrarily make up WKT, right? So you're gonna either build the data, potentially by using geocoding, which is the process of taking a textual address, such as like 1234 Oak Street, and turning it into a latitude and longitude. And there's services out there like, for example, Bing and Google that have a REST API, and they have traditional SOAP-based APIs as well to do that geocoding. Or you can do reverse geocoding, which basically takes your latitude and longitude and gives you a best guess of what street you're closest to. So that's one way to get, and traditionally I would say a lot of your application data is probably going to be point data, and you're probably going to get it by geocoding. So what I mean by this is you probably have a customer list, and that customer has an address. So what you'll probably do is go out and geocode all those addresses to get the latitude and longitude data. And then what you'll do is you'll probably have a sales territory. So you'll probably work with, for example, your salespeople, and they'll define their sales territory. And they may use postal codes to define those, or they may, if they're more advanced, they may actually like have a shapefile or a drawing of that actual region. And so you'll need to turn that into a polygon. And then you can perform all sorts of analysis to analyze customers versus territories, and do all sorts of sales and marketing analysis. Same thing kind of applies when you're looking at like retail locations, right? Or where do I start up a new store? Or if I have an existing store, where are sales pour from, and where would I put marketing money? What zip codes would I send direct marketing to? The other way to get this data is to buy it, and of course the way you buy data from the federal and local government is by paying your taxes, because they have to put this data up on their website for free. So the thing to search for there is census data or Tiger data, and that's all those shape files that I got to load the subdivision, the landmark data, the zip code data. All that stuff came from the Tiger data source. There's also commercial providers. So Azure Data Market has a couple providers that provide some different data, as well as ESRI or ESRI has this ArcGIS Online where they provide what they call base maps, and then they have shape files that have attribute data. And we'll talk about that stuff a little bit more. So getting right into the geocoding, again, we're just converting either textual addresses into coordinates or coordinates into textual addresses. And then the way to get good results is by using address verification processes and standardization. And that's a whole other kind of data quality topic. But if you Google those two terms, it kind of talks about that. A big vendor in that space is Melissa Data. for address verification. And all you're doing with address verification is you're sending out an address and you're saying, is this a valid address or not? And the verification service will give you a confidence level, or it'll say, yes, it's valid, or we think it's valid, and here's how confident we are that it's valid. And then standardization just refers to, imagine if you're going to send a physical letter to someone, there's a certain way you address it, right? So if you have all these addresses that are inputted in non-standard formats or incomplete, your results, it's going to be garbage in, garbage out, right? And so then the APIs that you'd use to do the geocoding are, again, Bing Maps REST services or the Google Places API. And they have a lot of other interesting functionality, and I'll actually show you guys a demo of how to interact with those APIs. So that's geocoding, and there goes PowerPoint again, so we'll just let it die. Okay, where were we? Geocoding. Okay, codes from current. Okay, so this is just another thing. I just put this in here because I thought it was kind of interesting. And there's a lot of information around these codes, but basically what you have is different standards bodies like Federal Information Processing Standards or ISO standards that ship lists of country codes and polygons, and then it goes down to the state level, county level, and then postal code. And it's just important to know that these codes exist and how to get them so you're not pulling just random stuff off the internet that isn't right. So some of the common formats, we've already talked about WKT and well-known binary. You have GML, ESRI shapefiles, KML, and GeoJSON is kind of the newcomer. So we'll look at well-known text. We've kind of seen some examples. And this is just how it's represented. So for a point, line, string, or polygon, you would just encode the data like this and process it. Notice that there's no SRID here. So if you're going to take data in as WKT, the other piece you need to make that data complete is the spatial reference identifier, the SRID. And you'd have to store that somewhere because you don't, when you create an object from WKT, in SQL Server, you have to pass that SRID in. So if you're, for example, getting WKT or WKB from an XML message, you're going to want an attribute column on the WKT column that encodes the SRID with it. And then for more information about these, there's a good Wikipedia page, which is actually where I got this imagery from. And there's also the WKT standard by OGC, and that link will get you there. So GML, again, it's an XML-based standard. It's OGC, and it just basically defines polygons, the outer boundary. You can put points in there. Notice here we've got multiple features. So we've got a polygon, a point, and a line string, and it's an XML way of storing it. GML is very, I won't say complicated, but it's very robust. And so KML, GeoJSON, no, I said that wrong. KML really simplifies it a little bit. Although the built-in support is for GML, I'd suggest using KML, especially if you're going to integrate with Google Earth. And a lot of the GIS products understand both GML and KML too. So ESRI shapefiles. So it's not really a single file, it's a set of files. So you have a main file, index file, attribute table, and project file. And you need all these components with the exception the project file is optional. That just tells you how the data is projected. But as long as you have the DBF file and the SHP file, most utilities will be able to read these. And so you can bring this in a tool like ArcGIS, or a lot of the open source GIS tools can read shape files. SQL Server doesn't provide a native way to load shape files, and we'll talk. I'll show you guys a utility that you can use shape files. The other way to do that is to write some .NET code that actually understands how to load a shape file. Some people have had luck just loading the DBF data, which is the attribute data, because it's a DBase format with SSIS, but then you actually have to dig into the shape file and find all the different polygons in here. So KML, or Keyhole Markup Language, it's an XML notation. It's an OGC standard now. It hasn't always been. And it's a much simpler way. Basically, it's a document. It contains different place marks with metadata like a name, a description, and then a geometric representation. So in this case, we've got a point object. It can store polygons, and it can contain styling information so that if I wanted to render this point in blue, I could put some kind of CSS-like styling information to it, and it'll render that. More information in the links here. GeoJSON is kind of the newer format. It uses JSON or JavaScript object notation. It's not an OGC standard. It was actually conceived of by an internet working group. There's geojson.org website where they show you the specification for it. This is really good if you're doing a lot of SPA applications or single-page applications and you're just using JavaScript on the client side. What you would want to do is return the data from SQL Server or from a web service as GeoJSON, and then there's JavaScript libraries that can process this and render it out on maps. So just an example. The big thing with JavaScript, JavaScript notation versus XML is you notice it's a lot cleaner of a markup. There's less angle brackets. There's less kind of cruft in there. So that's why kind of all the cool kids like Gabe and other people are kind of moving towards the JSON formats and away from the XML. But XML's been around for so long that it's pretty entrenched as well. So we talked about loading the shapefile. This is a screenshot of this Shape2SQL utility. And if you just search for Shape2SQL, you can find the guy's website. It's not open source, but you can download the binaries. And you basically point it at a shapefile. So here's my subdivision shapefile. I gave it a database server information, and I told it to load it as a geometry object, truncate or drop and recreate the table. Didn't set the SRID here, but I could have. And then create a spatial index. And then here's all the textual metadata that it'll bring along. And then I told it that the geometry field name is polygon, and the unique identifier is ID. And this, you basically click this upload button, and it uploads the data into SQL Server. So that's the way most people, because most people don't need to load shapefiles like daily. They just have it. They have its reference data. So that for one-time purposes, this is fine. If you need to do it daily or hourly as part of a cycle, you could certainly create a PowerShell wrapper or a DOS batch wrapper around Shape2SQL to do that. You could use SSIS or C#. You create a C# utility, which is what the Shape2SQL is actually written in. Or there's third-party utilities like ESRI produces one that will actually load shapefiles. So the hard part sometimes is getting the data into SQL Server. Then once you do, it's really easy to exploit it. So let's go ahead and go back to the demos and look and see what we've got here. So we had the question about indexing. And I'll show you there's some metadata views here that you can get metadata about indexing. So for geometry and geography, the functionality in the indexing is a little bit different. Since I have geography, it's going to use a geography grid tessellation scheme. Tessellation is just how do I chunk up the spatial data. Notice I can't specify the bounding box in geography, whereas I can in geometry, and that's my first tip. If you're working with geometry and it's localized to a certain area, if you set these bounding box minimums, that'll help the efficiency of your index, but you can't do that for geography. The other performance tip that we'll look at is there's 4 different levels. In SQL Server 2012, there's this auto grid feature where they actually use 8 levels of indexing. Basically, the levels have 3 values, low, medium, or high, and that determines how many sub-slices each piece is cut up into, and that determines how big your index is, basically. So obviously, at higher resolution, your index is more efficient, but it's a larger index. So there's a trade-off there, and oftentimes to, not performance tune an index, but to optimize a spatial index, you play with the grid levels and setting the high, medium, and low. So to show that, I'll give you guys an example of how. So here's just the syntax for creating these. So I've created one that was all high. I've created one that was all low. You can disable them just like you can a normal index. And then I will go through here and very quickly, because I know we're running out of time. set statistics IO and statistics time on, and I've got this real basic query I'm going to run. Now notice here I'm going to provide an index hint, and I'm actually going to take this one out. Now I'm only putting this hint in where did I get that? Shoot, hang on a second. I'm only putting that hint in just to drive home a point with the, what table are we at here? With the, just to show you guys I'm forcing the index. Normally, as long as you follow certain rules, the indexes will be used automatically. But here's what happens if we just do a straight clustered index scan with the index. You're going to notice it's going to take a really long time. And in fact, what I should have done up here, let's see if that goes through. It's already on. Here's the execution plan. Now, it looks like a pretty good execution plan, right? We've got a clustered index scan. We'd probably want to seek, so on and so forth. If we look at the messages, look at the CPU time, 31 milliseconds. And then, but notice it's just one scan, 21 logical reads. How expensive can that be, right? Or sorry, it's still going actually. This is the execution for this query. Apologize for that. So that's not a good execution time, as you can see. I mean, we're going on over a minute. There it is. All right, we got 135 rows back, one scan, 223 logical reads, right? Whole heck of a lot of CPU time was burnt. Okay. Now, I'm going to switch that. Also notice that there were no physical reads. That's important because what I'm going to show you with this performance improvement is that it's not the case that it brought the data into the buffer pool. It's actually the case that where's my index? That the data was already in the buffer pool. But this index, even though the query plan is going to look a lot more complex, it's going to go lickety-split. We're already done. So that's a pretty significant boost, right? Now look at the execution plan. Where is that? There we go. So you can see that it's using a spatial index here because it's going to do the clustered index seek spatial. And this, you're just getting a warning here. You can ignore that. Usually that's a point that there's a problem with statistics estimation. In this case, there's no statistics maintained on the spatial index. And then, so that's just, it's basically just a red herring. But this index, this query plan looks really complex, right? And these operators are 6 and 32%, pretty significant. Well, if we take a look here at our data, well, we've got no scans, we've got 460 reads, so less reads on, or sorry, more reads on the table. Look at the scan count, 1065 and 3,108 reads. In this case, we did have physical reads because of the index. Even so, look how quicker that executed. So the point I'm trying to drive home here is the way you define that spatial index for point data is pretty important in terms of your query performance. I mean, that's several orders of magnitude faster. And that included a penalty for the physical reads. If I run this again, it's probably going to be a lot well, not a lot faster because it was millisecond execution, but in terms of CPU time, it's going to be a lot faster. So that's part of it. The other thing too is the simpler you can make your polygons in terms of having less vertices or less, kind of jaggies in them, the more efficiently the indexing is going to help you. And I'll show you why here. Let's just before we do that, let's just look at this. So just visualizing spatial data. Here's an example of me using the Bing Maps control to render this polygon of the country Mali in the continent of Africa. And then these are some of our targets that we were trying to collect. So the blue ones are the collected targets, and the light ones with the borders are uncollected. So you have tile layers, which is this raster data back here, point layers, which are points, which I'm not using here, and then polygon layers here. And it supports shapefiles and spatial queries, but that's not really the point of this presentation. So spatial indexes, so they can be used to speed the queries significantly. There's several restrictions, though. This just talks about the grids, right? So the density and how many cells we have in the index. So what it does is it's a B-tree index structure that uses tessellation, to reduce the amount of rows needed to scan and the number of filters. So there's a bunch of rules, but we're running kind of short of time. The key thing I want to show you is there's only certain methods here that are, oh, that was geometry. There's only certain methods, so intersects or distance, that can actually support the use of spatial indexes. And then they need to be in a certain format, so it needs to be equal to 1. You can't say, you know, not equal to 1. That'll basically preclude you from using a spatial index. So you want to make sure you use certain query formats, and that's all outlined in some of the references I have. All it's doing is it's doing a two-paths filter. So the primary filter is going through, it'll return false positives, and then on that result set, it'll eliminate from that smaller subset of the overall data the false positives. So that's why our scan count was so high, right? And so we looked at these catalog views, and then there's a tuning sprock, SP help spatial indexes, and those can be used to kind of visualize your spatial indexes and provide some tuning insight. So that's spatial indexes. So real quick, I know we're almost out of time. I did want to show, since this is app dev, and we haven't shown any app dev yet, a program. So I've got a couple things going on here. The first thing is I'm going to use SQL Server data types inside my .NET application here. So I'm going to reference system.data.sql types, which is built into the .NET framework. And then I'm going to have to go find this Microsoft SQL Server.types. And there's versions for SQL Server 2012 and SQL Server 2008. Now in my case, the version was installed under Program Files x86, Microsoft SQL Server 110 SDK assemblies, and you can't see it here, but SQL Server.types. So I referenced that. Oops, I referenced that .NET assembly, right? I also brought in the SQL Server Spatial Tools, which is an open source project on CodePlex that some of the PMs for the Microsoft Server Spatial team created. And I used that because they have a KML processing routine. And then I also downloaded some code from the Pro Spatial 2012 book that does geocoding. So all I'm doing here is I'm creating a polygon for some WKT. Notice here I'm using actual SQL Server geography data types and calling the same methods I have in SQL Server from .NET. And then I'm going to use this KML functions, which is from this SQL Server Spatial Tools, to export this data out to KML. And then I'm just going to dump it to the console. Obviously, in your application, you do something a lot more fancy with it. I'm going to write that out. Then I'm going to go through here and I'm going to pass in some address information. This happens to be my address information. I'm going to go into this user-defined functions geocode library, which is in this Pro Spatial Tools from Chapter 6. Now this is all downloadable on the APress code site, but I'd highly recommend buying the book as well because it's a really good book. Covers spatial basically from soup to nuts. So all you do here is you call this geocode, you pass in the information, you get results back from it. I parse out from the XML results the latitude, the longitude, and then I write it out. And the next thing I do is I convert it to KML. Okay, so if I go through and do this with any luck, I apologize, I know this is kind of suboptimal, but basically what you see here is here's my KML output with my place mark and my coordinates from my polygon. Okay, And then here's my geocode result for my address. There's my lat and longitude. Now what I could turn around and do is go back and store that in my SQL Server table. Then I've transformed it into KML here, created a place mark, and notice it says exported from SQL Server. Point data here, and I've got my coordinates, my lat and my long, and I'm done. So that just shows how you can access this from .NET. It's pretty simple then to also access it from, for example, PowerShell, just by loading these modules, or you know, any other .NET-based language, like if it's F# or if anybody's using VB.NET, so on and so forth. So that's really the app dev side of it. There are a couple other open source projects that relate to .NET and spatial data, and you can search for those out on CodeFlex. They're out there. So just some references. The white paper that talked more about the spatial coordinate systems is pretty good. The Books Online Spatial Indexing Overview is another good one. And then the new features, which we didn't talk about a whole lot in Denali or in SQL Server 2012, there's a pretty good white paper that covers all the new features. So basically everything I showed you guys today, for the most part, can be done in 2008 or 2012. And then the books that I would recommend are if you're using SQL Server 2012, the Pro Spatial with SQL Server 2012. Even if you're not, I'd still say you can get this book because 80% of the content in here is still going to be relevant. The beginning version of this book, that's SQL Server 2008, covers a lot of the similar content, but I think the Pro SQL Spatial 2012 definitely gave a lot more advanced topics. And then there's a really great chapter in this T-SQL programming book that was written by Itzhak Ben-Gan, but the people that contributed to the spatial chapter were Isaac Kunin and Ed Kadaba, which were at the time the PMs for the spatial function in the engine. And it gives a really good, about an 80-page treatment on spatial data that basically just shows you how to get going, how to do some queries, how to do indexing, create tables, so on and so forth. So those are the references I'd recommend. And I guess we could take some questions if we have time, Gabe, or otherwise I guess we're out of time.
Yeah, we pretty much are out of time, but there's still some people on here, and there's one question that was asked regarding are we able to create virtual projections for games? Do you have anything you can shine light on that?
Yeah, for sure. So that's a really good question, actually, and I didn't talk about it because there's so much to cover. But you could potentially create your own projected, so not a geographic projected, but a projected coordinate system. Create your own spatial reference table to store that metadata of that coordinate system, and then SQL Server, when you give us, one thing I didn't touch on is geometries. They don't need to have a SRID, so they can have a null SRID or an invalid SRID. So you could create your own SRID. There's actually a certain range that you'd want to use so you don't conflict with any of the EPSG SRIDs. Assign a SRID from that, and then use that coordinates. In fact, in the OGC Simple Features spec, there's actually a specification for positioning text using geometry. Because if you think about it, your Windows desktop screen is basically a geometry, right? It's got X and Y's, and then it's even got Z values in terms of, you know, this window's on top of this other window. And so the math that does those calculations is the same math that we're using to do the spatial calculations. So another good example of that is, imagine what's going on right now, right? It's Black Friday, Amazon's getting all these crazy orders in, and they've got these huge distribution centers, right? So imagine if they had done some spatial analysis and laid their warehouse out and correlated routes that were really efficient for order or for items that tended to be picked together, or put, for example, packing or you know, put different warehouse stocks in certain shelves, and then the computer could calculate, given a given order, what's the optimal route for somebody to go pick this order. And so the person doesn't even have to know where the stuff is, right? They could have a handheld device that just walks through the order. I mean, furthermore, I don't know if you guys saw the thing with the Amazon delivery droids, which was pretty cool, but imagine that they now have machines that drive around inside their warehouse picking the data out of the warehouse and getting it ready for shipment, right? So they could do that. So all the way from delivery, or from from getting the order, they automate the picking of it, then they send it out to their little flying droids, right? And then the droids go out and drop it off at your house. So that's a pretty cool use of spatial. The other place that people use spatial is in CAD and CAM for computer machining and stuff like that. So it's really there's a broad range of applications. So I kind of went off on a little tangent there, but I think that shows the robustness of using spatial data for kind of non-traditional things.
Yeah, that's a great story with the Amazon droid. Probes, actually, right?
Well, drones. They're drones, right?
Drones, yeah.
Droids. These are not the droids you're looking for.
Another question, actually, just regarding your SQL scripts. Are you going to provide those somewhere where they can be shared?
Yeah, I can put those up. I can put them up on SkyDrive, and Gabe, I can send you a link later, and you guys can load them or download them and get them. I can take a stab at dumping out the data, and then I can put pointers to where I got those shape files too, so you guys can kind of do your own experiments with the data.
Mm-hmm. Great.
Cool.
Great.
All right.
Pretty much it. I guess if you have a chance to load up your contact information, if anyone has any other further questions or concerns, they can contact you. So.
And just again, here's my email address, here's my Twitter, and then if you want to connect to me on LinkedIn, just mention the AppDevVC as where you saw me, because I get a lot of really weird connection requests. So I try to filter that a bit, but I'd be happy to connect with you if you guys sat through the pain of this session. Apologies for all the PowerPoint crashes. I don't know what's going on with that.
Great. Well, thank you, Jason, and thank you, everybody, and hopefully we'll see you all next month at our next meeting.
Cool.
Right.
Thanks, guys.
Thank you.